Okay, so as promised, we're finally going to look at analog and RF layout today. Okay, so because especially because all of you said you have not looked at it. I know some of you are doing your masters in this area, so you probably have some idea, right? So you have probably taped out some chips. You probably know what kind of techniques to follow. So otherwise, so today I'll give a general introduction, and maybe next class we'll do an example, maybe a couple of examples. Maybe we'll do an op amp and maybe like a VCO or something like that. Okay, something simple. Okay. So first of all, what do you guys understand by layout? Does anybody know? Placing the transistors on what? On the substrate. Okay, so the layout is basically a representation of, you're right, of the transistor. Okay, it is basically the top view of the chip as you look at it. Okay, so you are basically going to give dimensions, let's say between devices. You're going to give the, let's say, things like the number of fingers, the width, overall width, the width of each finger, the length of the transistor. All of those things are going to be specified in geometrical patterns. Okay, and so far for example in let's say your devices course, you would have looked at the side view of the transistor, because that's what makes sense there, because you want to look at the current flow from the drain to source and so on. Whereas here it makes sense to look at the top view. Okay, because you want to look at the relative placement of the devices. You want to, let's say, control the orientation of the devices. You want to control how far apart they are, so you want to know how to route from one device to the other and so on. Okay, so that is what the layout is. And at the end of the day, what happens is you draw the layout using a particular tool, then you generate a file which gets sent to the foundry. So what the foundry does is, using that, they regenerate the layout and they create the masks for processing, for the wafer processing. Okay, that's typically, the mask will be an image inversion, right, a mirror inversion of the layout you send them. Okay, so for example, the typical, let's just take transistor like this, right? So drain, gate, source and bulk. Okay, so a typical top view, I think we have looked at this a little bit before, but a top view could look like this. Okay, so this is the gate. Okay, so obviously, so the gate is made of polysilicon. Okay, so now you need to contact to the gate. So what you'll do is, you'll extend out the gate, then you'll put in a contact. So it goes from, the contact takes it's a kind of via which goes from either diffusion or poly to the particular metal layer you want, typically metal 1, let's say in this case. So then you can route it out and connect it to a different transistor, maybe the output of the previous stage. Similarly, so let us say this is the source. Let us say this is the drain. Okay, how about the bulk? The bulk is the surrounding area. Okay, so typically your bulk is connected to, let's say for an NMOS, it's connected to ground. Okay, so what you need to do is, so put in contacts and connect it physically to ground. Okay, so let's say the ground goes like this. So let's say the ground line goes across like this. Okay, a typical layout could look like this. And remember that these bulk contacts are very important, because those are typically things people tend to forget or add it as an afterthought, but it is extremely important. So if you have a digital transistor, you may get away with putting let's say if you are building a gate, you may get away with putting a very, very thin or small contact, but in analog or RF layouts, you have to give a really good connection to the bulk. Okay, obviously, because a lot of things depend on the bulk voltage. So if you have parasitics, for example, if you have bulk currents flowing, Okay, you could have threshold voltage shifts, you could have a number of things happening. Okay, so you have to be very careful about that. And if you want to correlate with this with the side view, so first of all, this is the, let's assume a single finger transistor. So this is the width of the transistor, and so let me name the gate here. This is the length of the transistor. So effectively what's happening is, actually let me make it, that's okay, yeah. So again, this is your length, that's your gate. Okay. So let's say one of these is your drain, other is your source, and you have your bulk here. Okay. So your drain and source go like that, and this is where these contacts go in here. Okay. So the side view kind of looks like that, and of course the bulk contacts, you are putting it on the sides. So this is where you put in your bulk contacts. Okay. So first of all, what you need to understand is, you need to understand why you need to know layout. Okay. Why do you think you need to know layout of the transistor? So what you will find is, the layout of the transistor has a very big impact on the actual on the way the transistor behaves. Okay. So what we are going to see today, for example, the number of fingers will have a effect on the capacitance. Okay, on the parasitic capacitance. Similarly, it will have a slightly lesser effect on the GM of the transistor. Okay. So for example, if you have a single finger transistor with a length of 10 with a width of 10 microns versus a two finger transistor with a length of 5 micron with a width of 5 microns, definitely the GM is going to be slightly different. It will be different to a second order, but it will definitely be different. Okay. And what you design or what you lay out is what you are actually going to get. Okay, as long as the transistor is modeled correctly. Okay, so you should be very careful. And one of the things is, anything which affects the circuit performance, as a designer, it is going to be your problem. Okay, if you go to the industry, for example, you are working for a company, and let's say there are several companies where the designers do their own layout. Okay, so they are responsible for the end-to-end design. Okay, there are other companies where the designer designs a circuit, then the layout engineer layouts the circuit, and then of course the designer operates on that, make sure that, so at the end of the day the designer is still in control. Okay, so he's the one who has to direct the layout engineer. So typically the way it works is, the designer, before the layout engineer starts working on it, first of all the designer needs to design the circuit such that it can be laid out directly. Okay, preferably giving some information on the signal flow, because the layout engineer will typically not know a lot about the design of the circuit itself. He won't know which lines are critical. So what you will have to do as a designer is, let's say do what is called a floor plan. Okay, so you already decide where each device goes, how things are going to be routed. Okay, and then you sit down and tell the layout guy. So all he does is he basically draws out whatever you tell him, and he'll occasionally consult with you. Once it's done, it comes back, you look at it, give him some feedback on what lines to change. Okay, so eventually until it's perfectly the way you want it. Okay, so that's one of the primary reasons why you need to know how to do layout. Okay, and typically if you tape out a chip, you'll definitely learn how to do it. Okay, either from your own seniors or from your professor, from whoever. Okay, but as you'll typically be expected to know these things. So if you have, for example, interviews with companies, you can either expect it directly, direct questions on how you would lay out certain things, or once you join the company, they'll probably expect you to know layout. Okay, enough to at least direct the direct a layout engineer. Okay, so the other reason, so obviously the responsibility is with the designer. The other important reason you need to know is things like noise coupling. So there will be noise coupling effects. For example, if you place one circuit close to the other, or if you place one transistor close to the other, if one is noisy, the other is not, you could have coupling between the two, okay, because you always have finite isolation between two different blocks. Okay, so you need to know what to place close, what to route, in which direction, and so on. Okay, the other important thing to know is the amount of time you spend on these things. If you look at a modern, let's say an RF design, okay, only 50% of the time is actually spent in designing the circuit. The other 50% would probably be spent in laying out the circuit, especially if it's a very critical circuit. Okay. Okay, so let's say you're going to design an LNA and you're given, let's say, 3 months to do it. You'd probably spend only 1.5 months designing, or maybe 1 month. So first you'll start off with looking at what architecture is appropriate, then you'll try simulating it, and finally you'll come up with a good design. Then finally what you'll find out is you lay it out, then there is a step where you actually find out how good the layout is, and we're going to talk about that today. So once you find out how good the layout is, you'll find that it has a lot of issues, so there will be a lot of iterations between design to layout. So you'll have to tweak your design to make sure it can be laid out properly. Okay, so let's say the number of fingers, very simple example, number of fingers is not appropriate, you see too much capacitance, then you need to go back and change the number of fingers. Okay, so those kind of things. So you'll find that 50% of the time is spent on layout. One of the main reasons you want to do that is because once you lay out and extract the performance of the circuit, that is typically as close to what you will finally measure once you get back the circuit chip from fabrication. Okay, so you want to do the best things you can before you tape out the chip, because obviously taping out the chip is a very expensive proposition. Okay, it's going to cost tens of thousands of dollars. Okay, so that's another reason why you need to know about layout. So what are the general considerations? First of all, if you want to do layout, so you need to know what are called design rules. Okay, so design rules will typically tell you, for example, how close something can be placed to another. So all of these design rules are in place because the foundry or the process engineer wants to maintain the integrity of the process. Okay, so he cannot tell you, obviously, if you place it super close to two metal lines, he cannot guarantee to you that he cannot guarantee that those two lines will not touch once the chip is fabricated. So he'll give you a minimum spacing between the two, or he might give you a minimum enclosure around the via. So if you're connecting two metal lines, he'll tell you the enclosure around the via should be so much, because otherwise the via may not be connected to the metal properly. Okay, so those are all things which will come under design rules. So there will typically be geometric rules. Okay. Okay. So when you do design rules, so you go through something called what is called a DRC, or a design rule check. Okay, so it's an automated process where you do the layout, you send it, you apply the design rule check on it, and it basically tells you what all things are wrong. It will tell you this, it will flag. Okay, that's pretty straightforward. Then you do something called LVS. This is called layout versus schematic. So what this does is, let's say you have forgotten to connect the bulk of a transistor. Okay, when you lay out, you don't want to send it off to the foundry like that, because the transistor is not going to work properly. Okay, so this one, what it does is, it compares the electrical connections between the schematic and your layout, and make sure that things are exactly as the way you want. Okay, things are exactly the way you want it. Okay. Then there is something called ERC. Okay, these are all part of what is called physical verification. Okay, so all of these. So actually, we are going to look at a couple of others. ERC is electrical rule check. Okay, so for example, let's say a lot of modern analog processes or even digital processes have two power supplies. So they'll have a what is called a thin oxide transistor. So if you take a 65 nanometer process, for example, or a 130 nanometer process, you'll have a transistor which is minimum length is 130 nanometer and its gate oxide thickness is a certain amount, and you'll also have what are called IO transistors. Okay, those will typically be larger. So the minimum length on those may be like, let's say, 0.25 microns. Okay, 250 nanometers, and the corresponding oxide width will be thicker. Okay, corresponding voltage supply will be higher for those transistors. For the 0.13 micron transistor, we are using 1.2 volts. The other one may be, let's say, 2.5 volts or 2 volts. Okay, what happens if you connect a 2 volt supply by mistake to a 1.3 volt transistor? It's going to blow. Okay, the gate will blow. Typically, the gate will blow. Okay, because that usually has the lowest breakdown voltages. Okay, and similarly, if you connect a thick oxide transistor or the IO transistor to a low power supply, okay, what happens? You may design it for a certain resistance or a certain GM, right? And your VGS is going to be different from what you wanted to apply. Okay, so a transistor may have a lower GM, or it may not. If you're using it as a switch, it may not turn on enough. Okay, so again let's say you're trying to use it as an inverter. Okay, obviously it may not be enough to turn on the next stage. Okay, it may be at the threshold voltage. Say if you take 1.2 and 2.5, if the output is just at 1.2, it won't be enough to turn on the next stage. Okay, so those are all things which will be taken care of by ERC. It will check if a thick oxide is connected to low voltage or thin oxide is connected to high voltage. It will check indirect paths, direct paths. It will do all kinds of things. Okay. Okay, so then the other thing is, it is typically okay. It is done. It can be done on both. Okay, it can be done on both, and ideally it should be done on both. Okay, because at the design stage, if you have by mistake connected something wrongly, you want to find out at that stage. Okay, so there is a version of ERC which is done at the design stage itself on the schematic. However, the more complete check is done on the layout. Okay, the more complete check is done on the layout. LPE is what is called layout parasitic extraction. So what do you want to? What does this thing do? So in the schematic, if you connect one line, one node to the other, it is an ideal connection. Okay, so it's an ideal wire. Can carry as much current. It has zero resistance, zero parasitic capacitance, and so on. But in real life, we know that's not true. Okay, so if you have a metal line, it is going to have a certain resistance, capacitance, and so on. Okay, so this layout parasitic extraction, what it does is it extracts parasitics from your layout. So this is typically done on the layout. Okay, so a typical example is, so let's just take in the schematic. Let's say if you have an inverter driving another inverter. This is how you do it. You'll probably have ideal VDDs, grounds, and so on. Okay. Whereas in the let's say this is in, what you actually have is more like something like this. You actually have something like this, because any connection you make between the two is going to have and quite possibly you could have L here also, but the reason I have not shown it is I am assuming you are going to place them close to each other. They will definitely have resistance and capacitance, but probably inductance doesn't matter too much. But usually the power supplies and the ground lines are routed a long distance, so they will have resistance, inductance, and probably capacitance also. I am not shown it here, but they will have capacitance. Okay. So a real connection would look like this. So this is the actual circuit you are going to measure in the in the lab. So you want to model those things. So what the LPE tool does is it generates these parasitics for you. So you can do either just RC parasitic extraction. So there are different levels. Okay. So you can do just capacitance. Let's say your resistance doesn't matter too much. You can just do capacitance level extraction. Okay. And then you can do RC. So typically you would want to do capacitance level first to make sure capacitance don't affect you too much. Then next level is to do RC extraction. Okay. RC. So capacitance level extraction will tell you things like, let's say the slope of your signal will get degraded if you add more capacitance. Okay, because your circuit will not be able to slew if you take an inverter. Okay, so that just simple capacitance extraction will tell you. If you do RC extraction, it will tell you things like whether there are bandwidth limitations. Okay, you are trying to send a signal along a certain line. Is it really too resistive or too capacitive? There's going to be an RC bandwidth. So this will tell you if you do an RC extraction. Again, there are circuits where inductance is very critical. Okay, simple case, you just take any amplifier, any large signal amplifier, even an inverter, let's say. Okay, if you add a large inductance, and which is definitely going to exist in real life, if you add a large inductance in the supply or ground parts and try to simulate it, you will see all kinds of weird stuff going on. Okay, that itself will tell you that inductance is very important. Okay, so you can do one more level, which is inductance extraction. Or if you have a very long signal which is being routed, let's say 1 millimeter across the chip, an RF signal, 1 gigahertz, 2 gigahertz signal, so you need to take care of inductive parasitics also, because depending on the inductance value you will get things like peaking. Okay, depending on inductance and the Q. Okay, so you will see obviously transmission line distributed effects. Those are all things which you want to model. So that's why you want to do this LPE. Okay, and obviously this is a very important step, because LPE is typically where you will find out issues with your layout. Okay, so design the circuit, layout, LPE, simulate, and then you will see degradation. You will go back, modify the layout, so you can find out where the layout gets spoiled, where the design gets is most sensitive to layout. Okay. So let's look at a few simple techniques. Okay, maybe as we go along, we'll look at more advanced, maybe more core RF techniques. But by and large, the techniques used in whether it's an analog design or RF design is very similar. Okay, but there are some things which you can do with analog which you can't do RF. There are something which you have to do with RF which you may not do with analog. But it's good to know both kinds of techniques. Okay. So obviously this we have seen before, which is multi-finger transistors. We looked at this briefly before, right? During, I think before you started the LNA design, LNA project, we looked at this briefly, but let's look at it again. So let's take a single transistor of width W, and let's say we are going to call this dimension E. Okay, for now you will see why, because that's actually quite significant. And let's say this is your drain, this is your source, this is your gate. Okay, and of course this is your L. So of course if you just look at the schematic, this transistor is going to look something like this. Okay, it's going to be your gate, and you can also draw this transistor like this, where let's say we go to a 2-finger transistor. This is W over 2. This is again E. Okay, so that E does not change, because remember Okay, so you have some parasitic capacitance on the drain and the source, and you typically want to minimize these parasitic capacitances. Okay, so what you want to do is you want to keep the drain and source diffusion areas as small as possible. Okay, so what that means is you just want to make it wide enough such that you can put in some metal contacts. Okay, and that's pretty much as wide as you want to make it. There may be cases where you may be limited by things like current density. Okay, so that is another important thing we have not looked at yet, but current density is actually quite important because a real metal line can only carry so much current. So the foundry will tell you if you are routing on this metal layer, it can only carry so much current. So per micron of width, okay, it can carry, they'll tell you, it can carry 1 milliamp or 2 milliamps, okay, maybe half a milliamp. It all depends on the material of the metal which is used to create that layer, the thickness of that metal layer, and so on. Okay, so those are all things which are very important, and there may be cases where you really want to widen out this E, because if the transistor is operating at a very high current density, you might want to have a very wide, more number of contacts and more number of, again, by the way, contacts also have current density requirements. Okay, so you may want to have more number of contacts in some cases, but in most cases, let's say we'll just consider, okay, and let's say if you want to, you normally prefer to do it this way. Okay, so this is basically, actually let's draw it slightly differently. So this would be an equivalent circuit of what this is actually what you're doing. You basically have two transistors in parallel. The only difference is you're actually sharing the drain diffusion between the two transistors. Okay, so that's what this is. So let's call this A and let's call this B. So what is the difference between A and B? So first, yes. It actually depends. Okay, some processes are very sensitive to this E, other processes are not. Okay, you have to be careful with that. You're right, but there are, if you look at most of the long channel processes, the E is actually wide enough such that you don't have a problem. The VT shifts have come with these later, like very deep submicron processes. Like if you go to 65 nanometer, for example, you'll see a very big change. Okay, and that's why the rules will also force you to have some certain amount of minimum distance and so on, such that you want to keep VT shifts to minimum. Okay, so let's look at what kind of capacitances do you have. Okay, so you're interested in, let's say, drain bulk and source bulk capacitances. The other things are all, for example, gate drain and so on, or source drain, they are all related to your overlap gate, and gate drain or gate source overlap capacitances. So you can't do too much about them. That's limited by the process. Okay, but the junction capacitances, you can do something about them. Okay, so if you look at these junction capacitances, they actually have two components. Okay, so let's look at the I can just use the old layout. Okay, let's look at this guy. What kind of capacitances can you think of? So obviously, if you're looking at drain to bulk, there's a capacitance here. Okay, and source bulk capacitance is here. So that is the junction capacitance. Okay, that is the bottom capacitance. Okay, and you also have a component on the what is called the side wall. So because it's basically like a trench, okay, and bulk surrounds it all around. Okay, so you'll have two components. If you look at the drain bulk capacitance, what does it depend on? So obviously it depends on the area, right? So if you look at the drain bulk capacitance, it depends on this E. So it depends on the bottom area. Okay, so it depends on E and it depends on the width of each finger, W. So you have okay. So you have two components, and We know this, right? How about the sidewall capacitance? Sidewall capacitance is actually proportional to the sidewall area, which is a product of W and actually the depth of the diffusion. And the depth of the diffusion is a constant for a particular process. Okay, so effectively you can say that it is just proportional to the width W. Okay. So what you will find is the parameters which are used to represent, let's say, per unit capacitances. So Cj will be let's say so many femtofarad per micron squared, because that will be the constant. Okay, whereas this will be just CjSW times certain width. Okay, so now let's calculate the total capacitances for these two structures. Okay, have you guys done this before in any of the analog courses, for example? No? Okay, because this is something which is used quite often, done in the basic analog course, but if you have not done it, I'll do it here. Okay, so if you take the case of A, let's just look at CDB and CSB. Let's look at both. So CDBA, which is the same as CSBA because it's a completely symmetrical structure. Okay, so you have, which is the bottom component. Okay, so now the sidewall component is going to be proportional to the perimeter. Okay, and so you're going to have a component proportional to E also, which is the other sidewall components. We looked at the two sidewall components on the left and right side. You're going to have towards you and away from you, you're going to have two more capacitances, and that is going to depend on the length parameter on this side, which is E. Is that clear to everyone? Pretty straightforward. Okay. Right? So it's going to depend on the perimeter. Yes. Okay. This length is E, right? So if you just take the drain, you have an E component here, you have an E component here, you have a W component here, you have a W component here. So it's going to be 2 into W plus E. Right? No. That is going to be for the drain. For the source, it will have the exact same component. Right? You are talking about the drain and the source? Okay. Yeah, so you're talking about this E and this E. So okay, let's go back here to this guy. Okay. So you're going to have a component proportional to W on that side. So remember that this is W. Okay. You're going to have a component proportional to W on this side. Right? It's basically like a trench. Imagine a trench which is running along lengthwise. So you're going to have a component W here, that's the width. And then there's going to be a component here and there's going to be a component there. Those are the four sides. And this side is going to be proportional to E, that side is going to be proportional to E. So you're going to have 2 times W and 2 times E. Right? How about the second case? Now in the second case, obviously now your drain and source are no longer symmetric. The way we have done it is that the drain is actually lower area, so you would expect it to have lower capacitance. And in a typical circuit, that's what you would want. Okay, normal, let's say common source amplifier, you would want it this way. Okay, what is your CDBB? Width is W over 2. Okay, so you have W over 2, right, times, let's say this is still E. Okay, so it's proportional to that area, W over 2 times E, and Cj is the constant for that process. Plus, how about the sidewall component? Again, the perimeter times Cj SW. Okay. Source bulk capacitance, you have 2W by 2 times E. So because you have two sets of diffusions, plus you have 2 into okay. So you'll have basically your let me put it this way. Okay, so let's write in a slightly different way. So let's just do the single one and multiply it by 2. Okay, so you have 2, each one is W by 2 times E times Cj, that is the junction capacitance, plus what is the sidewall capacitance? So for each of these guys, you have W by 2 plus E times 2, correct? That's the overall perimeter. Right? Okay. So obviously your CSB is a little bit higher, especially a sidewall component. It's a little bit larger, but your drain bulk capacitance is a lot lower. Okay. And this is of course obviously the primary reason why you want to do it this way. If you do, more number of fingers, you will get some extra help with your drain. It won't be as large as going from 1 to 2, but you will get some extra help. Okay. We looked at gate resistance, RG. I think we talked about this when you do your when you did your LNA project, right? Obviously, your gate resistance will now go down because instead of one single long gate, you have 2 gates in parallel. If you look at it as a very crude, if you just represent each gate by a bulk resistance, which is not correct, but if you say the total resistance of the gate is actually RG, what happens here? You have RG by 2 because it's proportional to the length, and those two are in parallel. So to a crude estimate, it becomes 1/4 the original resistance. In reality, that's not true because the actual gate resistance is a distributed quantity. Okay, just like this transistor is actually there's a transistor along all the way. Each signal sees a different resistance. So there is an expression in terms of the number of fingers, but this is the it will go approximately as RG over 4 for 2 fingers. And remember, this will be a function of your poly resistance, okay, your polysilicon resistance, and usually this will be given as so many ohms per square. Okay, typically you define it as a sheet resistance. Okay, so in general would be proportional to 1 over number of fingers. That is normal. It will be some function of it. It will go as if it's inversely proportional to that. Okay. The other thing you need to know, okay, so let's say you need to connect your gate. So make sure do not route on poly. Okay, any connection you want to make it on metal. Okay, go immediately from poly to metal and then route it on metal. The reason is your poly resistance will be much larger than your metal resistance. Okay, metal will be the least resistive. So you want to do all connections on metal. Okay, there are certain cases where people do poly connections, and those are done for standard cell gates. Okay, you will see standard cell gates where, you know, for example, if somebody is building an ASIC and they want to do an auto place and route for, let's say, involving millions of gates. Okay, which means each gate should be laid out as efficiently as possible. And once you have thousands of gates, anyways, you know, timing and other things are become limited by number of gates rather than, you know, they will be limited by the what do you call it, the delay of each gate. But at some level, you can play around with the timing at a higher level. Okay, so people do for standard cell gates, they do route on poly because they want to make it extremely compact. Okay, if you want to cram in a million gates, you can't. If each one is just a little bit larger, it will just grow quite a lot. Okay, but in analog layouts, never route on poly. Okay. Routing with poly, not routing over poly. I am saying don't route with poly. Okay. Now we are going to come to, you know, what metal you can use to route what. Maybe I don't know if we'll have time to come to it this class. Definitely next class we'll come to it. Okay. About what metal you can use to route which signal, for example. Okay. There will be cases where you need to make a choice because all these modern processes will have 5 or 6 metal layers. Okay. How about the drain source resistance? Again, so if that is critical, you will have to be careful about, maybe you want to, here we just looked at, here we just looked at a single layer. You can, for example, have multiple layers in parallel. For example, if this was metal 1, you can have metal 1 and metal 2 routing in parallel. Okay, so that is one thing you can do. You can make the same thing wider. Now the only thing you have to be careful when you do all these things is you have to worry about parasitic capacitances. Okay, and typically these parasitic capacitances will be to the gate, okay, or to adjacent lines, and these things may not be modeled very well. Okay, you have to be a little bit careful because that even your LPE step, right, layout parasitic extraction step, there may be cases where these, for example, capacitances on top of the transistor to the gate, there have been cases where people have got burnt. Okay, they didn't you know, set the switch properly, and then, you know, you get completely crazy result. Okay, as in you do your LPE simulation, looks fine, but you get back your chip, your gain is maybe 6 dB lower, half the gain. Okay, things like that have happened. Okay, so be very careful about this. And apart from that, wider metal layers, metal lines. Yes.
We are modeling means we are saying that modeling itself is not there, or just selected the wrong switch.
Okay, the thing is, these kinds of parasitic capacitance may not be something. Okay, remember that everything you extract, it only increases your simulation time as you do the LPE. Okay, so there may be certain small parasitic capacitance which you don't care about. Okay, and you know, there may be certain cases where you really don't care about these capacitances. Okay, it may not be the thing which is really limiting your performance, and typically for most you know, mixed signal designs, you may not worry too much about this capacitor. Okay, but there may be certain cases, definitely RF cases, you would worry about this capacitor, and there are definitely, you know, some important cases where you have to be careful. If you're building a high speed ADC or something, you really have to be careful about these things. Okay.
Sir, you told one advantage of splitting the transfer into so
yes.
Is it like you will split it as possible into the relevant?
No, remember that the GM is also a function of your number of fingers. If you make your, you know, transistor too small, okay, there are two things you have to remember. One is GM, okay. The other thing is, if you make the transistor too small, what you're effectively doing is, for a given, let's say for each of those fingers, you have to worry about, let's say, the gain or performance GM, whatever you're worried about of that particular cell versus the extra parasitics you're adding by actually splitting it into number of fingers. Because definitely by splitting it into, let's say, these number of fingers, if you add more number of fingers, you have to worry about how to connect. Okay, so let's say you split it up like this, something like this. Now you have to worry about routing these sources. Okay, So you have to worry about routing it like this, and you have to worry about routing it like this. This may add some extra capacitance, resistance, and so on. Okay, and if you make it too small and too long, you are basically routing this a long way. Drain source, you are routing your gate a long way. So those are all trade-offs you'll have to make when you decide how many fingers you want. Okay, I would say a good rule of thumb is, let's say WF is the width of each finger. Try to keep it. Okay, try to keep it somewhere in between these two. 1 to 5 microns. If you have very large transistors, you would probably want to tend towards the larger limit, towards 5 microns. Okay, otherwise your aspect ratio will get very weird. If you have very small transistors, let us say the overall width is only, let's say 10 microns, you're not going to gain a lot by making it into like 1 micron fingers 10, you'll get a very long finger again. Okay, so you probably want to have a trade-off, but keep it somewhere in between these two numbers. Okay, obviously there are cases where if the transistor is not in the signal path, you don't care too much. Okay, if your gate resistance is not particularly significant, let's say if you have a control line which you're using an inverter in the control line, you really don't care. Okay. Interdigitization. So let's take the case of a diff pair. So you have a common source. Okay. Let's say there are some certain number of fingers you're going to choose. So you're going to have D1S, D2S, and so on. Okay. In the earlier case, we looked at multiple fingers being used for a single transistor. Here, if two transistors, for example, share a common node, in this case a common source node, you can try to, for example, you want to reduce the parasitic capacitance at this node. Okay, remember that for the mixer, classic example. Okay, you want to reduce, if these are the switches, you want to reduce the parasitic capacitance. So for those switches, what you're going to do is you're going to share the sources. Drain capacitance, you don't care too much because you're actually having an RC filter for a receive mixer. Okay, so you may want to do something like this, and of course now you'll have to connect these guys. So obviously this would be your D1 again, so you'll probably have to do something to connect these guys, so that I want, no, whatever. Okay, you'll have to connect those guys, but you'd want to do something like this. Is called interdigitization. So what you're doing is, if you look at the gate connections, okay, so let's call this M1, M2, this is actually M1, this is actually M2, M1, M2, and so on. You have alternate M1, M2 transistors. So one of the main reasons why you want to do this, so you want to have, so let's say if you have a diff pair, you know there are a lot of quantities which depend on the matching between these two transistors. Okay, starting all the way from, if you take analog cases, offsets, right, or if you take RF cases, you have things like, you know, if you take your mixer for example, you have things like LO rejection or your RF rejection and so on. Those are all things which will depend on the matching between the two differential paths. So you have to be very careful. If you just lay it out as two huge bulks and you don't know which way the wafer is going into your let's say your inside the furnace. Okay, so what that means is there will be temperature gradients. Similarly, your let's say they're doing some deposition of the dopant, it will come from a certain direction, you don't know, it may not be uniform. Those are all things you have to worry about when you want matching, and if you do something like this, those kind of effects will be distributed out. Okay, so if it, and this kind of layout will take care of, for example, left and right orientation. Okay, so if you have temperature gradients in this direction, it will be taken care of, this either these two directions, or if you have process related, okay, doping, those will be taken care of by this interdigitization. Another case where you might want to have it is, so let's say take off a cascode. Okay, you have a common source drain node here, you would want to do the same thing. You want to, you know, for example, if you have an LNA, if you have any parasitic capacitance here, so your VRF is here, IRF flows like this, you want all of that current to flow here. So you want to minimize the parasitic capacitance at that node. You don't want to lose any signal through this path. Okay, so you want to minimize it, so you definitely want to interdigitate and reduce the capacitance. Okay. Other techniques for symmetry. So we saw that interdigitization takes care of sideways, right? So if you have something, you know, sideways temperature gradients, it takes care of it. But there are cases where you have to, I mean, obviously you don't know which direction the wafer is going to be processed, right? So you have to worry about, you know, gradients in all directions. So you can do what is called common centroid. Okay, which is you now split the and you can combine all of these things. For example, so you split it into 4 sections, and each one of these can be interdigitated. Okay, so this common centroid can be used in conjunction with the previous technique. And now what happens? So let's say this is 1, 1, 2, and 2. So now if you have, let's say, in the y direction or the x direction, if you have gradients, part of the transistor will get it, part of the transistor will not, right? Will get a lower effect. So this thing is called the common centroid. It's quite common. Now the only thing you have to be very careful about is this is very layout intensive, because now let's say this was, you had to connect out these gates. Okay, so now you have to route the gates, you have to route the source and drain connections. So it's actually very intensive. Okay. And I would say in RF layouts, it's only of limited value. Okay, it's only of limited value in RF layouts. Okay, but I mean, like I said, there's always an exception. You may find a case where you might want to use it. So let's call this A. Okay, obviously other very basic things. Okay, orientation. Obviously, if you want to match 2 transistors, let's say one was like this, you're not going to make the other like this, that's for sure. Okay, that's very stupid, right? So you're definitely going to make sure they have the same orientation, right? Dummies. Okay, so remember, so one of the things you have to know is, so let's say this was your gate, right? You're trying to, let's say, do the source drain diffusion. This is actually done at an angle, okay, of something like 7 degrees from the vertical axis. So which means you actually have something called shadowing. Okay. So you have to worry about this, because if you just place them next to each other, one of the transistors could shadow the other transistor. Okay, so if you just place them like this, okay, in this case I have shown, okay, let me show it slightly more. Okay, so obviously one transistor could shadow the other. Okay, so now if you want to make it very slightly better, you can do it this way. I mean, I have shown it rotated, but what you understand what I mean. Okay, so obviously the shadowing is not going to affect the other transistor. Okay, so they're horizontally placed, so the diffusion is going to come from this side. Okay, remember, so since it's coming at an angle, there will be okay, so since let's say it's coming from this direction, so this transistor lies in the shadow of this the second transistor. Okay, so you will have some gradient. Okay, and this kind of thing will prevent that. So I mean, okay, obviously you can also draw it like this. I just drew it sideways, but you can draw it like this. That's what I mean. Okay, placing one below the other. Yeah, but remember, if you want to, if it comes from this direction, you'll have much less shadowing because the gate is longitudinal. So what you want to do is make sure the gates are in the same direction. That's what I mean. Actually, we are going to look at that. Okay, what we are talking about is dummies. Okay, so the other thing you can do, which is actually slightly better, is, so let's say you have two transistors, you can actually put in what are called dummies on either side. So even if you have shadowing, so this will be 1 and 2, the transistors you are interested in. So even if you experience shadowing for this guy, you will experience shadowing for this guy also. If it comes from the other direction, again the same thing. Okay, any direction you have, the dummies will take care of it. And in reality, you want to have dummies in all directions. So let's say your transistor, in this case I have shown a very simple array. So let's say you have something like this. So your transistor is laid out in 9 sections. Okay, you probably want to have dummies in all directions actually. Okay, you want to have something like this such that it's protected on all sides, and ideally these dummies will be identical to your main transistor section. So every transistor in all directions will see the same number of devices and the same environment.